This is Unit 12, Lesson 1, and in this unit we are going to start, well actually, yeah, looking at statistics. So pretty much just looking at, sorry, I said open the window. All right, looking at statistics, so just analyzing data, all right, and how it's spread out and finding averages and stuff like that. So this is a continuation of some of the stats you did in Algebra 1, but the main thing we're going to focus on is the normal curve. You may have also referred as the bell curve, okay? So there are 4 characteristics to the normal curve. The first being that it is bell-shaped and it's symmetrical about the mean. All right, here's the general shape of it. If you're looking at a scale, okay, it's bell curved and the mean is smack dab in the middle. So if we were to fold it in half, the 2 sides would match it perfectly. All right, now also the mean, median, and mode are equal. So all of them are right there at that middle center line. It's important to know that when you're drawing it, that your axes or that the curve never touches the x-axis. Why? Because what we are doing is we're actually going to be finding the area under the curve. All right, so dealing with probability, percents, and all that good stuff. The area under the curve, the area under the curve is 1. All right, because the area is probability. So the probability of something occurring, if it's under the curve, is 1 whole. If we change that to a percent, it's 100%. So 100% of the data must fall under the curve. Where it falls, that's what we're going to get into today. Okay, so things that you would normally make normal distributions. Just some small examples would be the LDL cholesterol levels in adults. So if you were to survey a sample size big enough and chart the actual cholesterol levels, it would make a bell-shaped. IQ scores, SAT and ACT scores, pretty much any standardized testing. If you were to, now if we sample size, took 2 people's scores and did it, obviously that's not going to be a curve shape, but if we had enough people's scores, it's going to make that curve shape, where you have the middle of the average, people above and people below. The further to the right the bell curve goes, the less people fall there, and same thing in the other direction. And then also anything you can find in nature actually follows the bell curve. The width of the stripes on a zebra, the acidity of the rainfall, okay, the length of time it takes milk to spoil, all that good stuff. So all of these things would make a curve with the 4 characteristics that we just listed above. So what makes them different though? If they're all making a curve, how do I know what I'm looking at? Well, one thing would be where that median or mean line is located. So what's going to shift that? How do I know if it's, further to the left or to the right? It depends on the scale that you're using. Okay, so the scale size, the numbers that you're measuring. An SAT is measured out of 1,600 points. The average, I think, is typically somewhere in the 1,000 to 1,100 range. The ACTs is out of 38, I want to say. It's somewhere in the 30s. I think it's 38. So looking at those, they're obviously not going to fall on the same, they're not going to use the same scale when I draw numbers on my axis because, I'm looking at 1200s, I'm looking at 32s. Okay, so that's going to be what's going to shift it around sideways on your scale. Depends on really what the sample is. The second thing is going to be the standard deviation. And we're going to take a more in-depth look at this on the next page. All right, the standard deviation is going to determine how short, wide, tall, and fat. It's going to determine the shape. Okay, so what is standard deviation? So remember, the standard deviation is how much something changes and how far away from it the mean it is. Okay, so the standard normal curve has mu equal to 0. That means the mean is 0. This means mean right here. And the standard deviation is 1. So that's your standard normal curve. If I'm just taking a look at a curve and I haven't actually assigned a scenario to it and we're not labeling our axes like we will shortly, your mean is right here in the middle and the standard deviation goes by 1. Okay, it's kind of like your parent function. We can transform it. We can shift things around. We can make it taller, skinnier, etc. Now, remember, your standard deviation, that's the same thing as your z-score if you think about what you did back in Algebra 1. If it's a positive number, it's above average. It's to the right of the mean. If the standard deviation is negative, it's below average and to the left of the mean. Okay? The closer it is to 0, the closer that number is to average, to the mean. And just a reminder, the area under the curve is 1, always 1. So let's compare normal curves now. So it says the following rectangle has an area of 1 because it's 1 unit wide and 1 unit tall. So 1 times 1 is 1, yay. On the same axis, draw a rectangle with an area of 1 and a width of 2. So the area has to stay the same, but the width is going to double. So if my area has to still be 1, 2 times what would give me 1? That is correct, 1/2. Okay, so those two shapes have different dimensions, but the same area. So what we can conclude is if the two rectangles have the same area, the width and the height are inversely proportional. As one dimension gets bigger, the other gets smaller and vice versa. So a taller rectangle must also, so the taller it gets, so if I were to cut this in by 1/2, all right, or double it up to 2, the width would be 1/2. So the taller it is, the narrower or skinnier, whichever you want to use to help you remember, it is to have the same area. And this one should say shorter, sorry. So therefore, we can conclude a shorter rectangle must be wider in order for the area to maintain the same value. So it's the same true for the normal curves. Okay, the area under the curve must be 1. So the bigger the standard deviation, okay, the more spread out the data is going to be. So the wider it is, that must also mean it has to be shorter in order for the areas to stay the same. If the standard deviation is closer together, it's going to be skinnier, so therefore it must be taller. As one dimension changes, the other one changes in the other direction. All right, let's take a look at a situation now. We still have our normal curve, but we're going to actually label it and talk about something here. So the average height for men is 5'9" with a standard deviation of 3 inches. Okay, so we can go ahead and label it. 5'9" is in the middle. Now I'm adding 3 inches every time I go to the right at 1 standard deviation. And then I'm subtracting 3 inches every time I go to the left. Okay, now we can say the heights of American women have an average of 5'4" with a standard deviation of 2.75. So their their average is right here. Okay, it's a lot, sorry, right there. It's a lot farther to the left. Now, their standard deviation is going to be smaller as well. It's going to be like here, and here. All right, and for right now, I'm just making marks. So the point being, the standard deviation is smaller, therefore it's going to be a little bit narrower. If it's going to be a little bit more narrow, it's got to be a little bit more taller, okay? And the mean is farther to the left. So we said it has to be skinnier, and that's because the standard deviation is smaller. So that makes it skinnier, and when it's skinnier, it's also going to be taller. So let's actually compare some. So what we're going to do is just draw some examples. It says draw a curve that has the same mean and a smaller standard deviation. So let's first figure out if it needs to shift sideways at all, and then figure out the shape. If it has the same mean, the average is staying right here, it's not moving. Since it's a smaller standard deviation, it's going to be skinnier. Since it's going to be skinnier, it's also going to be taller. Okay, now we don't have a scale here, we're kind of just sketching it in. So anything that looks like that, that works. Sorry for coughing, guys. All right, the next one, the same standard deviation and a smaller mean. So since it's a smaller mean, it's moving to the left. So I'll put anywhere. We don't have numbers. We're just, getting an idea. To the left, same standard deviation means same shape. So just do your best to make it like the same height and width. Okay. Good. A larger mean and the same standard deviation. So a bigger average means it's moving to the right. Same standard deviation means same shape. So it's going to be over here somewhere. It's supposed to be in the middle. It's the board. A larger average, so moving to the right. Smaller standard deviation. So smaller standard deviation closer together, so skinnier and taller. And moving it to the right. So like, woo, something like that. Larger standard deviation, same mean. So it's staying where it is. Larger standard deviation means it's more spread out. Okay, so it's going to be wider and shorter. So like that with mean in the same spot. Oops. So it says the following normal curve shows the weights of Doritos and Cheetos. What can we decide about them? All right, well, I can talk about the mean, so the average weight of the bag, and how spread out the data is. So I can conclude that the Doritos, on average, weigh less. And the weight is more variable. Okay, there's a wider range. It's not as, it's a little more spread out. You also could have said it from the Cheeto point of view. Like you could have said the Cheetos, on average, weigh more, and they're a little bit more reliable. There's not as much variance in how much their bags weigh. Either way is fine. All right, let's move on. Okay, so the empirical rule. So now we're going to figure out, well, what the area under the curve is for each one. Okay, right now we're just going to look at what happens when it lies on the standard deviation. So what I'm telling you is that in a normal distribution, 68% of the data lies within one standard deviation. So from here to here, that's 68% of the data. So that's that's more than half. That's a good chunk. Fall within one standard deviation. When we say within one, we mean one on each side. Okay, in a normal distribution, 95 falls within 2%. Or I'm sorry, 2 standard deviations. So from here to here is 95. And then 99.7 fall within 3. Now, you got to keep in mind there's still another 0.3 that don't fall within 3 standard deviations. So we have to account for that data. So what we can actually do is we can label each little chunk right here. So let's go ahead and do that using those 3 numbers. That's all we need. So 68% are within here. Remember, this is symmetrical. Therefore, I can divide that by 2. 34% of the data is within each of those. Or the area under the curve is 0.34, changing it to a decimal. Since from here to here is 95, okay, to figure out these two, I can go ahead and take my 95, subtract 68, what we already know, and divide it by 2 because it's symmetrical. So that means 13.5% is in each of these pieces. 99.7 lies within 3 standard deviations. Okay, so once again, to find those, I can just do 99.7 minus 95, what I already know, and divide it by 2. And you should get 2.35. So that means 2.35% of the data falls within here. All right, now we said there's a 0.3 left over, so 100% of the data is on the curve. I don't know where those other values are. They could be outliers. They could be right next door within 4 standard deviations. They could be super far away. But in the entire curve, I need 100%. So keeping that in mind, if I do 100 divided by, minus the 99.7 divided by 2, I get 0.3. So 0.15% of the data is somewhere outside. Okay, but I do need to take into account the 100%. So you don't have to memorize the smaller numbers. As long as you know the 3 bigger numbers in your empirical rule, you can easily find the percentage within each chunk. All right, so let's do a problem with this. So we're talking about men's height again. Okay, so we talked about this earlier. I'm just doing 5.9. We know it's 5'9", so don't be like, oh, you get the point. Okay, so 6 feet, 6.3, 6.6, 5.6, 5.3, and 5 feet. So what is the probability that man chosen is going to be over 5'9"? So that's from here and over. Now, guys, I can go ahead and I can add up all those pieces from here. Okay, 34 plus 13.5 plus a 2.35 plus 0.15, or I can just realize since the 5'9" is the average, I'm just looking at half of the graph. So that's 50%. However, when I'm asked for probability or area, I'm asking for a decimal. So I don't want to write 50%, I want to write 0.5. And then when I ask for the percentage, I can say 50%. All right, now I'm being asked, okay, well, how many? How many people is that? So I'm going to take the total number of people surveyed, which was the 1,000, and I can multiply it by the area. So total times area for whenever I'm asked how many. So 0.5 times 1,000 is 500. So 500 people fall within there. So now I'm being asked from 5'6" to 6 feet. Okay, that's within 1 standard deviation. I looked up at my scale right here and I saw the 5.6 and the 6 feet. So I'm going from 1 to 1, -1 to +1 standard deviation. Well, we remember that was 68%. Okay, so that's all I need to do. Woohoo, go us. So between 5'6" and 6'3", so I'm going from -1 standard deviation to a +2. Okay, so we got to use our percentages now. So we had 34 here, 34, and then between 1 and 2 is 13.5. So once again, if you didn't remember that, you can just find the pieces and add them. I think it is easier to try to remember the smaller numbers like the 34s as opposed to 68, but it's up to you. So when I add all those up, I get 0.815. It's asking for probability, so that's why I wrote it as 0.815, not 81.5%. Now, how many? So I'm going to multiply that by the total number surveyed, which is 1,000, and I get 815. Okay, now we're doing less than 5'6" and over 6'3". I'm going to come up to this one up here because it's a little bit easier to see. Less than 5'6" is right here, or over 6'3" is right here. So these pieces were 2.35 plus that 0.15 that we had to account for. Here I've got 13.5, and I'm adding the 2.35 and the 0.15. So when I add all of those up, I should get 0.185. Or if you noticed, I'm asking you in number 8 the opposite of 7. So since the total, or opposite of 6, I should say, since the total area under the curve is 1, I could have just done 1 minus 0.815 since I already found that and got the 0.185. Okay, so there's different ways you can think about it. How many men are under 5'6"? Well, we already looked at those numbers. These are these right here. So when I add those up, it's 13.5 plus 2.5, which is 0.16. I'm asking for how many, so I'm going to multiply that by 1,000. Give me 160 men. The last thing I'm going to do is percentile. So it says a man who is 5'6" is in the what percentile? Okay, percentile means it's just find the percent. Okay, that's all it's asking. So I found the decimal, which was 0.16. I changed it to a percent. So it's the 16th percentile. So that tells me that a person that's 5'6" is taller than 16% of the other people that are surveyed. So when I'm asking for percentile, I'm really just asking for the percent, and we can write the TH or the ST depending on what the word, for 31st to be 31st percentile. Okay, so percentile is just percent. All right, that is all. Please watch lesson 2 before you do the practice. It'll tie it all together.